Okay, the final section is on 8.4, the system security. And as I said, it's all about imperfect design and implementations of the system. If the system design implementation are perfect, then no such issues. I mean, for system security. So when hackers need to want to attack a system, it would first of all, you need to do information gathering, and usually by these techniques, so-called scanning, sniffing, snooping, and social engineering. The scanning is to scan the port number. The port number. Why scanning the port number? Because most of the vulnerabilities are based on the servers program, on the server programs, application server program, but much less on the kernel itself. Much less on the kernel itself. Mostly on the application servers. And as we have seen in chapter 5, the servers listen on what? Well-known ports, right? The server listen on well-known ports. So if I'm a hacker, what I would do is I would scan all the machines to check on which port they have server listening on. And then try to identify what kind of server and what kind of version is a program that listening on a particular port. So if I scan a server machine, I want to know which port from port 1 to port 1024. Okay, the possible well-known port. Which port have server listening on? And if I identify, okay, these 10 ports on this machine, 10 of the well-known ports have servers listening on. Then next, I want to identify what server program, what are the programs. For example, on port 80, is it Apache server or other server? If it's Apache server, what version of Apache server it is? And then I have a table summarizing for what server program, which version, it has certain vulnerability, and it can be attacked by a tool, a hacking tool. Okay, so I have a table summarizing the vulnerability of all kind of server program. Okay, and also I have a tool, I have a methodology or tool that can attack that vulnerability. So first of all, I need to understand what server program are running and which version they are, and then I look up the tool. Okay, saying okay, this particular version of this particular program has this vulnerability, and if you use this methodology or this tool, you can gain what? You can gain the root control. Okay, so then I issue the attack. So first of all, I need to identify all this, doing information gathering, and sniffing is to sniff the packet, to try to get some either the information about the server or some password that they have been exchanging. Or social snooping, that and social engineering try to ask around. Okay, so we will not skip this too much detail on scanning. Okay, one possible, as I said, if we have identified what kind of servers are running on that port number, then what we can do is try to attack the vulnerability and gain the control of the server machine. One probably the most popular attack model that will gain you the control of the machine is the so-called buffer overflow attack. And it works in this way. Okay, if I have a server program with a function code, but in the server program, and it has a local parameter into this procedure. So this procedure has a parameter of this size. Okay. When this procedure is called within the server, what happens is on a stack, you will put the return address of this program. I mean, you have been called here, somewhere here. You will put the return address on a stack, and then you put the local variable and the parameter on the stack, and of course include the parameter on the stack. And the parameter is to be input when this procedure is called. Okay, and suppose as this is a server, so the parameter is to be some string that is input from the client program. So the client will issue a string, which is a protocol message string, to the server program, and the server program will pass to this function call as a parameter. Okay. So if I write this program and I don't do much check to see what has been passed as the parameter, I just receive it. Then it is possible that the client can put more data into the parameter that will cause the buffer overflow. So this is a buffer, the buffer that would accept the parameter input from the client, and it's only 200 bytes. And the client program has intentionally input a protocol message string which is longer than 200 bytes. In fact, so long that it would overflow and then overflow to erase or cover or overlap the return address. So then the return address has been rewritten when the client sends a protocol message. So when the client sends a protocol message, the server program, the server procedure here would take that protocol message and then put it into the buffer here. But since it's too long, it would overflow and overlap on this. Okay, so now the return address is gone, has been replaced by something else. And this something else might be some other program. Okay. So when they finish this procedural code, they will pop up and then pop up the return address and then jump to the return address. But now since the return address has been changed to this, it will pop up and jump. The CPU will jump to this particular address to execute. And that particular address might be something doing something else that the client wish the server to go through. Okay, so this is just a beginning of taking the control of the server machine. But as you can see, by doing buffer overflow, we can overflow to erase the return address. Okay, and forcing the CPU to jump to somewhere else. Okay, so this is one typical example of a server vulnerability. The programmer who wrote the server program didn't bother to check the input parameter, which is actually the protocol message from the client. Okay, is it clear? The buffer overflow, it's very typical. And as you can see here, here's some example of vulnerability that have been reported on different programs. These are all server programs. All of them are server programs. This one is about configuration. Okay, and many of the reasons here are buffer overflow. And it's very sensitive to which version, because in newer version it'll be fixed. In newer version they'll be fixed. But this kind of server vulnerability has become less and less effective for hackers, because now the server programmer are more aware of this. So they will do more checking, fixing more bugs. And so that's reason number one. The server programmer are more aware of doing the check to avoid the vulnerability, those kind of vulnerability. Reason number two is because right now the server we are running have been, many of the server, especially the popular server, are mature. And when they become mature, evolving into very the version number have been quite large. Say version 12.264. That's a lot of updates have happened on this particular program. So there'll be less and less vulnerability that can be attacked by the hackers. So, and of course you can attack some less well-known servers. But if they are less well-known servers, there will be much fewer targets to attack, because most of the servers are running some well-known server programs. And since they have been mature, so less and less vulnerability. In previous years, hackers are attacking server programs. But in recent years, they are not attacking server programs. Server are not the major targets. The major target now are the clients. But there are not many services or programs running on many port number. No. As we have seen in chapter 6, most of the client programs are running on what? Dynamic port number, not on the well-known port number. So the port number does not mean anything, and the port number would not the client running on the particular port number would not last very long, and it become less effective to attack the client port compared to attacking the server port. So attacking the client, the way to attack client is quite different from the way to attack server. The way to attack server is you proactively attack the scanned vulnerability, the vulnerability that have been scanned, that have been found. That's you proactively do the attack. But for the client, you solicit, you seduce the client to download malicious programs. So instead, you put some content on the internet, some program on the internet, which are malicious program, and seducing the client to download. Okay, and once they download and click, the backdoor program run and reside on the client machine. Okay, so in a sense that the server do not proactively attack the client. They distribute the malicious content, the malicious program on the internet. And then those malicious content and malicious program lying there passively waiting to be retrieved by the client. And then they reside and live in the client PC, in the client PC, probably forever, staying unnoticed. And what they do is that they collect private personal data from the client, and then send it out, reporting it back to the master, for example, or the controller, piece by piece, or in batch. So it's an evolution of how the hacker attack the vulnerability. At the beginning, as I said, they attack the server program because most of the vulnerability exist on the server program, and the server program are the major target. And as we have moved, as the server program have become more secure and with less vulnerabilities, and also as we move from Web 1.0 to Web 2.0, we have discussed in chapter 6 what Web 2.0 means, right? What Web 2.0 means is the client become visible, right? The client become visible, and client can provide resources to the community. So now client become the target, but they don't. It's difficult to attack the client directly because the client come and go, and the client program might not exist long, and it's difficult to scan all of them because their port number are dynamic. Okay, so instead of attacking them proactively, we attack them passively by distributing the malicious malware on the program for them to download. So if you go to P2P or on some search engine, you search for some interesting stuff, and then you found the content on web, on P2P, or you receive something interesting from mail. You click, and you got what you want. But in the meantime, a backdoor program has been downloaded and residing on your PC. And they will stay unnoticed for a long time. So, and they probably don't harm you immediately. They don't destroy, but they steal. They steal your personal data. They steal your directory, for example, your mail directory. They steal what friends you have. they steal your configuration file, personal file. I don't know. They wrap around. They could wrap around a lot of the entire directory and send it out slowly, because why slowly? They want to stay unnoticed. If they send quickly, you would notice that, saying, okay, I'm not doing any download, but how come my networking card is working heavily? Okay, so they would send out those stolen information and files silently, quietly, and slowly. Okay, that's the evolution into the recent years. Okay, there are some tricks, some other tricks like password cracking. There are some news report on the most popular password. That'll be what? ABC 1 2 3, and some English, some well commonly used English words. Okay, denial of service is another kind of attack. There have been a denial of service or distributed denial of service. What this kind of attack is not to break in. They do not intend to break in. They do not intend to steal information. So they don't intend to do this. What they intend to do is to bring you down, so that you cannot offer service. They don't want to steal something. They don't want to break in. They just want you to shut down and couldn't offer services anymore, at least for a period of time. And this kind of denial of service usually is done by sending a lot of traffic, to sending a lot of requests to the website. Okay, so that your resource have been exhausted. For example, if you run a restaurant and I just bring 100 people to stay in a line but do not order anything, then you couldn't run your business. And so one way to do this is called SYN frauding. SYN frauding with the IP spoofing. It means that I send the SYN. Remember in chapter 5, transport layer, in the TCP three-way handshake, you will need to send SYN, and then the server from the client and the server respond with SYN ACK, and the client send ACK to finish the connection setup, right? To finish the three-way connection setup. The first one is sending the SYN. And what if I send SYN to the client, to the server, and the server respond with SYN ACK, but I do not send the ACK back. I do not send the third protocol message back. It means that the server will stay. The server will stay waiting. The server will keep waiting for the third protocol message in order to finish the three-way handshake. In fact, as we discussed in chapter 5, there are two queues. One is the finished queue. One is unfinished queue for three-way handshake. So for all the connection, TCP connection that has not finished the three-way handshake, they will be put into the unfinished queue. And once they finish the three-way handshake, they will put into the finished queue. But because I hold the third message, so the request I send to the server will stay in the unfinished queue indefinitely. I don't send the third message. And if I send a lot of such SYN message, I send a lot of SYN. with a spoof source. With a spoof source, it means that the source IP address is not me, someone else. I fake the source IP address. I write it to someone else. So when it returns the SYN to somebody else, not to me. Okay, I send a lot of such SYN to the server. This certainly will fill up the queues at the server, the unfinished queue, incomplete queue in the server kernel. So that when there's a legitimate customer, the ordinary user, when they send a SYN message to the server, because the queue has been full, right, has been occupied, so the SYN sent from the client, the real client, will be dropped. So then the server would not be able to offer service to this client, which is a normal client. So if I send a lot of SYN message to the server by this kind of SYN frauding attack, the service will be shut down, cannot offer any service, because the queue there, the TCP queue there will be full. Okay, that's one popular attack. There are other attacks that would send either a lot of packet, or by just sending one particular packet. If I know the implementation of the server has a problem, if I send a particular message, it will hang. Then I send that message, and the server will hang, and then it would not be able to serve anymore. So it is also possible by sending just one packet to kill the server. Okay, not just the SYN frauding or sending a lot of packets to kill the server. It is possible to send one or just a few packets to kill the server if there are some particular vulnerability. Okay, DDoS is an extension of DOS where you, instead of just me doing the attack, I could recruit a lot of PC to do the attack together, so that we can pump enough packets. For example, I'm standing behind on the top, and I control a lot of PC, and at a certain time I issue command to ask all the PC to launch the attack. For example, SYN frauding attack to a particular server at the same time. So if the attack launch is set to be 6 p.m. September 11, then all the client will send the SYN frauding to the server together, and if it lasts for 1 hour, so during that particular 1 hour, the server will not be able to serve almost any client within 1 hour. So that's when the server capability is very high. If the server capability is very high, then it takes a group of clients to exhaust the resources of the server. Okay, but this kind of attack is becoming still happen occasionally now, and it has the effect of bringing down the server, but just for a short period of time. Okay, and the damage is not permanent; it's only for a short period of time. But can we detect and block such an attack? Okay. Yes, to some degree. For example, it is possible that if you sense that there have been too many SYN but without egg. Okay, syn with syn egg but no egg. Then you sense that there might be syn attack. Then you could block the syn from those particular sources. So it's possible. There have been some proposal on this, but they couldn't work perfectly well, but they work to some extent. Okay, malicious program or malware. Okay, so now we have covered the intrusion. Okay, but how about malicious? I mean, the vulnerability attack. But how about the malware and virus? It is a program. If I am the inspector of the network, okay, and if I'm the policeman, I will be watching on two things. One is crime on the scene, on the spot. They are shooting, they are fighting. Then I know it's crime. But I will be also noticing another scenario where people are carrying gun, carrying weapon on the road or in a car, right? They might not be doing crime, but they are carrying weapons that could lead to crime, right? So if we think the program, the malware is the weapon, okay, the malware is residing on a machine, okay, but it doesn't go live now. It means that the program is there, but not issuing attack, okay. But if it come alive, then it will be starting to sending attack traffic, okay. So we could, on the network, we can do two things. If we watch the traffic, we should watch two things. One is the attack traffic. It means that there is some people who is using the gun to shooting the other guys. So I'm watching the shooting. That's the intrusion. Or I should watch another thing, the traffic, within the traffic, I should watch. There are people passing by, but they are carrying the gun in their bag, in their pockets. But they are not doing the crime right now, but they are carrying the gun. So I should look at two things. One is the intrusion going live, the on-the-fly intrusion. The other will be the malicious program, which is called malware. That is in the packet being carried from side A to side B, being transferred. So actually, when we are looking at the malicious program here, there could be virus, worm, Trojan, backdoor, bot. These are if in the packet, within the packet, if there are this stuff, the malicious code, then we should be able to detect and maybe block. And because once this has been transferred to a new target, the new target might be able to send attack traffic. Okay, when this program runs, when this program are run, they will send attack traffic. So there are two kinds of traffic. The traffic that is the attack traffic, or the traffic that is carrying the malicious code. Okay. And either way, you will see that if I want to detect the attack, the intrusion, then you would use the solution is called intrusion detection or prevention. But if you want to detect the traffic which is transferring the weapon, the malicious program, then the solution is called anti-malware or antivirus. Okay, usually called antivirus or anti-malware. But they are doing the same. They are scanning the packet to see if there are malicious programs. And one such solution is called CLAM-AV. AV stands for antivirus. Antivirus. So it would scan the application payload. It would scan the application payload to look for the pattern, particular pattern. So either scanning the malware or virus or scanning the intrusion, they all need to depend on something called signatures. Signatures. For example, if you go to the airport and they are doing the immigration check on you and also your bag. So what they would do is that they have some signatures to check whether you have something malicious on you. Okay, they would check. If you are nervous, then it's possible that you have carried something malicious, right? So if you want to carry something, don't stay calm. Okay, that's one signature. And if you are, they use a X-ray scanner, scan your bag, and they use the metal detector to scan your body. So if you are carrying something metal, they will detect, because those weapons mostly are metal. So metal becomes a signature, right? So similarly, virus would have signatures. Intrusion have signature, and in particular, in virus, the signature database is usually very large. For example, in CLAM-AV, they have collected over 570,000 signatures. 570,000 signatures over the years. Okay. And each signature is usually long. It's mostly over 100 bytes. Mostly over 100 bytes. But how do they get a signature? They get a signature from the customer who claim that they have been infected. When a customer claims that they have been infected with some virus, they got the program and they inspect the program to see what's the unique feature of this particular program and compare it to the original program. And they find that, okay, this segment is different, and I grab a string from this segment to represent the signature, to take the signature as a representation of this virus. Okay. So then they need to do signature matching. In CLAM-AV, what they do is that they do signature matching. They load a signature from different files, and then in the runtime, when a packet comes, they do signature matching to scan the application payload to look for signature. So on one hand, I have packet application layer payload collected, reassembled. and I check against with my signature database to take the application payload to check against my signature database to see if they appear in my signature database. If they do, if the payload appear in my signature database, then it's a match. It's a match. It means that it has this particular virus. How about intrusion? That's the virus or malware. We rely on antivirus. The claim may be. But how about intrusion, which is a crime on the fly? Crime on the scene, which is they are shooting, they are stealing. It's a crime traffic, not a traffic carrying the weapon, but a traffic with the crime happening, with the attack traffic. Then we use the solution called IDS, Intrusion Detection System, and Snow is the most commonly used open source solution for intrusion detection. And within the Snow rule, it would check, for example, in this rule, it checked on HTTP. It checked on HTTP and saying, okay, if within the URL you have this, then it is a PHP probe, PHF probe. It's an attack. This is an attack traffic, and I would log a message saying this is a PHF probe. It's an attack. So I'm looking for the HTTP request to see if it has this signature. So compared to virus signature, which has over 100 bytes, the intrusion signature are usually short, only a few bytes, say 10 bytes. In this example, it's only how many bytes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bytes. 12 bytes in IDS is considered long enough. There are signatures which are short as 3 bytes or 5 bytes. Okay. Of course, when it goes, the signature goes shorter, the chance of having false positive is higher, right? When the signature becomes too short, the chance of having false positive is high. Okay. And for antivirus, because the signature is so long, over 100 bytes, so the chance of having false positive will be what? Almost zero. Almost zero. So for antivirus, you would hear false negative, but you wouldn't have false positive, because the signature, virus signature are long enough. But in IDS, you would hear a lot of false positive. Of course, also false negative, yes, but also a lot of false positive, because the signature usually are short. And in this example, it's only 12 bytes, and some other signatures are even much shorter, with 3 or 5 bytes. So you would say put rules saying what kind of traffic you want to inspect, and the source destination. This specify what kind of traffic you want to inspect, and then you specify the content, the signature. And this is considered as one snort rule, or one signature rule. And how many such rules you have in snort? I think about 10,000 rules now. 10,000, yes, 10,000 rule. 10,000 such rule right now. And each of them represent a particular attack traffic. Okay. And here's a block diagram of snort. It basically does reassembly and then do matching against the signature database. on the application header. Mostly on the application layer, but only a few on the application payload, but mostly on the application headers. There's another open source implementation in 8.8 span assertion, which is used to detect, block spam mail. It also does string matching, but with the Bayesian probability calculation. So I will skip this because it's not that related to security. If you consider spam, sometimes you don't consider spam as a security threat. Okay, here's a sidebar on performance matter comparing intrusion detection, antivirus, anti-spam, content filter, and P2P classification. And for intrusion detection, we test on Snort. For content filtering, we test on Dense Guardian. For antivirus, we test on Claim AV. For anti-spam, we test on spam assertion. For P2P classification, we test on L7 filters. And all of them rely on string matching. They all need to look at the application header or payloads. And they all need to do string matching, to do signature matching. And they all need to maintain signature database. And here it says that the percentage of string matching, the percentage of time spent on string matching. And as you can see, it's very high. Most of them are very high, except spam assertion. Mostly over 60, around 60% or above, except spam assertion. So they spend most of their time doing what? String matching. And where do they match? They match on header or payload. For example, Snort match are mostly on header, and Dense Guardian match mostly on they match mostly on the request, application request on the headers, and this are mostly on the response, and some on request. Client maybe need to look into the payload, application payload, especially the attachment in the application payload. Spam assertion look at the particular message body, just the mail message body. L7 filter look at the header messages. And you will see which one is the heaviest. It says the processing time per byte. It's normalized latency. Which one is highest? Antivirus. Why? Because every single byte needs to be scanned in the application payload. Because when we say deep packet inspection, it has different levels. It could be just the application header, or just the request. The header within the request, or the header within the response. Or it could be into the payload of the response. The payload of the response. And virus is well in the attached file. So it is usually deep in the application payload in the application response. Deep in the payload in the response traffic. So it's deeper, and every byte needs to be scanned. So for example, IDS it's not difficult to scale to over 100 megabit per second, or 200 megabit per second. It is not that difficult because you only need to compare. You only need to do string matching on what? On the header field, application header field. And it's only a few bytes, mostly. You don't need to scan deep into the payload. But antivirus, you need to scan deep into the payload. And there are so many bytes you need to scan. Okay, so if you normalize by the traffic passing through, then of course antivirus will be the highest. And you can see that intrusion detection is very small because not every byte needs to be scanned. Just a small percentage of byte in the header. I mean, just the bytes in the header need to be scanned. Application header, not application payload. So the percentage of byte being scanned will be small. That means the time spent on average over byte will be small.